Thank you so much for having me here. I've been working with Earth Species Project, and I'm super excited to talk about the progress so far, which is about using neural networks to represent audio signals without any supervision. So I have just one slide for myself. So my name is Masato, and I work as a independent artificial intelligence and machine learning researcher, which is a fancy way of saying I'm a freelancer. But I have my own kind of research lab, and I work with clients. And so my former employees and clients include Duolingo, the language learning app based in Pittsburgh, Pennsylvania, and ACT Next and AI2, which is stand for Allen Institute for Artificial Intelligence, which is based here in Seattle. So I have a PhD in AI and ML, and my focus has been on natural language processing, or NLP, which is a subfield of artificial intelligence for processing, analyzing, and even generating human languages. I published 4 books on machine learning and also NLP. So if you're interested, I can probably give you like a coupon code of some sort. Yeah, that's basically about me, and I can just go dive into the today's topic, which is word embeddings or embeddings. Um, what are word embeddings or what are embeddings in general? So they are just vectors, some mathematical representations of meanings of words. So here are a very simple example. There's a vector for this word cat, which is just a vector of 3 floating numbers, 0.7, 0.5, 0.1. I just came up with these numbers. So don't worry about like specific values of these numbers. And there's a vector for dog, which is 0.8, 0.3, 0.1, and a vector for pizza, 0.1, 0.2, and 0.8. So these are all 3-dimensional vectors of continuous values. So you can actually, because they are vectors, you can actually plot them in a vector space of 3 dimensions. So if you plot them on this XYZ axis, you have a vector for dog here, a cat here, and maybe pizza here. And these vectors are trained. So these vectors are calculated from a large database of language in such a way that if 2 words have similar meanings or similar semantics, they are close to each other in this vector space. And if they are, for example, these dog and cat vectors, and if they are not related, they are not close, like pizza. So that's the topic. And why do we want them? Like what can we use them for? There are a lot of applications and tasks where we can use those, like semantic representations of words. One is classification. So you can classify words based on where they are. So if you look at the vectors for dog and cat, they have higher X values. So say if any word has more than, the X value of any word is more than 0.5, for example, then you have a basically animal classifier. So you look at the values or where those points are, and you can tell a lot about what they actually mean. You can also use them for some linguistic analysis. If you have heard of part of speech analysis, which is to identify, what are the nouns and verbs and adjectives and so on in a sentence. And it helps a lot if you know the embeddings or use those numerical representations of words. Uh, Another one is called named entities, personal names, company names. People care about those proper nouns in a document, for example. So you can use those embeddings to identify what are the related concepts written in a document. And the focus of the topic and the ESP is translation. So why this is good for translation? Um, because you can actually map those embeddings on the vector space, and you can see how words in different languages correlate to each other. So there's a seminal paper from Facebook AI in 2018, which is this paper. So what they did is they translated words in two different languages without using any dictionaries, basically. So theoretically, if you have a huge database of English and if you have a huge database of, I don't know, an alien language, then you can plot the embeddings on this vector space and you can align them together. The basic assumption here is no matter what the language is, the structures of those points or vectors are have some similarity uh, between the languages. So in this plot on the left, you have embedding space for English, cat, car, and deep, and another space, another kind of structure is Italian, and then they kind of look the same. So what they did is they learned this mapping between these two subspaces in such a way that they actually overlap and indistinguishable from each other. So that way, if you look at this, the final plot, the point for cat and point for gatto are very close to each other. So we can actually see, oh, maybe this is the Italian translation of cat. So word embeddings are the building block for all sorts of natural language tasks and also decoding unknown languages. Yeah, so that's about word embeddings. Any questions, follow-ups so far?
Ideally, you'd want to work the inverse problem where you get meaning out. Meaning is not an input with humpback whales. So you don't get to put in meaning or whatever that creates a vector. All human languages have meanings for like sky and fish and things like that. But with humpback whale, you want to extract meaning by where it lands on the diagram, right? So
right.
What do you initially plot if you can't plot meaning for starters?
Yeah, that's a very good point. So the beauty of this method is it still works, even if you know nothing about the language or the data you're dealing with. So you're not giving any constraints. Like you're not giving any information about the data you're working on whatsoever. And the model or the algorithm just figures out, how to place those dots on this vector space.
Okay, that's what you mean by unsupervised.
Right, exactly. Yeah.
Okay.
So all you need is just a database of like just utterances or text or audio, and then the algorithm, just figures out how to plot this. Yeah, and that's actually what people do with like unknown languages or like endangered languages, even though they don't have like dictionaries or lexicons. they can just throw a bunch of data into this algorithm, and the algorithm gives you some information about how things are related.
So I have a question about that first step where you went from phrases to real valued vectors in some Euclidean space. And that metrizing, how, I mean, a number of questions come up. One is that metrizing, which is just kind of an arbitrary choice to start with, is that semantics preserving? In particular, the metrizing of the space is going to change the topology and the shapes you get. And then if you later on claim that similarities between languages depend on intrinsic shapes, then that really does depend on how you initially metrize the data.
Exactly, yeah. That's where neural networks come into the play. And we will have a neural network solve this problem. And we are making a lot of assumptions here. So neural networks are like basic computational models that have many inductive biases. Like they are basically metrics, multiplications, additions, normalizations, and stuff like that. So our assumption is you have like a layers of computation via a neural network, and you just come up with this number. And yeah, so that's the how we kind of metrize the semantics.
I mean, I guess that could be an argument. I'm looking for some sort of completeness, just like when we use Fourier representations of acoustic signals. We kind of rely on the fact that frequency-based representations are complete if we have enough Fourier modes, enough frequency modes involved. So I'm kind of looking for something that said, if you took a sufficiently large embedding space, and this is really what you see in support vector machines and all this other, what you do is you map into sufficiently high space, maybe even infinite dimensions, and then whatever kind of intrinsic nonlinearity actually gets linearized. Of course, you pay the price with the high dimensional spaces you're working in. So I'm kind of looking for some kind of statement that says that if I take the embedding, that initial metrizing into a sufficiently high space, then the neural network can find and kind of extract these statistical dependencies that maybe turn into these nonlinear shapes in lower dimension.
Yeah, that's a very good point. So the methods that I'm going to go over do not actually care if things are kind of recoverable or it can actually encode the information in such a way that it can actually encode all the information from the input. It's the main goal here is to just come up with nice representations of like words that you can use for downstream tasks. But there's I think I have to add that there's another kind of family of neural network models that are called autoencoders or variational autoencoders or VAEs that actually do care about mapping things like images, text into a vector space in such a way that they can actually reconstruct the original input. So yeah, so they care about, so those like VAEs models care about one, encoding, and two, a reconstruction from this embedded space. But in this work, we just care about the first step, just encoding. Yeah.
Thanks.
Yeah. I think I will move on. So yeah, as I mentioned briefly, we're gonna just have a neural network to do this. The whole architecture is super simple. You have the input, which is the audio of variable length. So it could be just 1 second of speech or maybe 10 seconds of some animal vocalization. It's variable length. So that's kind of tricky because neural networks are not super great at dealing with variable length input. But you have the encoder, what we call encoder, which basically takes this input and compresses this into some sort of a vector representation. And then at the end of this pipeline, you have this like a vector of a fixed length vector. So the length is predefined, like 100 dimensions or 200 dimensions, because it's a computer, you can deal with more than like 3 dimensions, although you cannot actually visualize them directly. So that's the That's a pipeline. So this leaves us two questions. One, what to use for this neural network? Like, what does this look like? Because you can't just throw a random, computation here to expect that, something useful comes out of this. So you have to design this. And two, how to train this. Because neural networks should be trained. They are just kind of like a black box with a bunch of tunable parameters, like numbers that you can tune. But the way these parameters get tuned is you have to give it some supervision, right? You have to compute the in a mathematical term, you have to compute the gradient, or how much to change each one of the parameters in such a way that this produces something useful. So those two aspects of this pipeline. So you have to, I'll get to them one by one. The first problem is how you design a neural network. And here we use something called CNN and RNN. CNN stands for convolutional neural network, and RNN is recurrent neural network. So this works like this. So you have the input, and first you convert this to some sort of feature representation, like a high dimensional representation of the audio. We use MFCC, or mel frequency capsule coefficients, I think what that means. And they are basically like a higher, like a meta representation of like frequency domains. They are like something like audio spectrograms, if you know what they are. So then you have basically an audio signal represented in this feature space, and for a word. So let's say the word is barking, as in a dog is barking. And in this work, we just assume that you know the boundaries of the word. So you know where the word begins and where the word ends. So you just take the clip of the section for the word, and you feed this into CNN, or the convolutional neural network. And then RNN, the recurrent neural network, processes this, and it gives you back this embedding. That's how this operates. And I just didn't want to go, deep dive into what neural networks, like how neural networks work and how CNNs, RNNs work. It just takes like, a 1 hour lecture, I think. To give you a very high level intuition as to what they are, CNN is something like a sliding window with a fixed pattern. You want to detect some pattern that is in the input, and the way this computes the output is you have this sliding window, and you just slide this over to the input, and you compute the inner product between this window and the input, and you get a value for each time step. So that's it. Super simple, but CNN is very popular, for computer vision tasks like image recognition, object detection, and even like self-driving cars. Like self-driving cars wouldn't run without CNNs. It's just a bunch of CNNs, layers after layers, and they can detect patterns in the video and in the image, like lines, edges, some textures, and even like human eyes, etc. So they are CNNs, and RNNs are something like a for loop in a programming language. It has a subroutine, and it gets applied to the input one by one. So the first subroutine computes takes the first input and then computes something and passes to the next one. And the next one, the same computation again receives the input and does something and passes it to the next one, and so on. And you just keep doing this until you exhaust. Yeah. Go ahead.
Choose the dimensions?
I'm sorry?
Does it choose the dimensions or do you?
We choose. It doesn't choose the dimension. Yeah.
Okay.
So these sizes, size of the dimensions and capacity of the neural networks, they are all predefined. And yeah, that's what the neural network looks like. And the second question is how to train them. So for training embeddings, we use something called distributional hypothesis. Which is pretty popular in linguistics, computational linguistics. The concept is pretty simple. If you look at the surrounding words in the same sentence, you can know a lot about the word itself. You can know a lot by its company, right? So if you have a sentence, I heard a dog barking in the distance, and let's say you have never seen this word barking before, like you're learning English and you don't know anything about barking. If you look at the sentence, you see heard, you see dog, and in the distance. So you know from this context that barking has something to do with hearing and something to do with dogs, and maybe something you can even hear from the distance. So the context has a lot of information about the words. So that's what we leverage here. So this is the only slide with any math, any stock. So I'm not going into the detail of any of this, but the concept is pretty simple. So let's say you want to train a nice embedding for this word barking, which is X, which is your target, and you have this go through the encoder, and it gives you back the embedding, which might not be what you're looking for. But anyway, it gives you back something. And you do the same to the surrounding words, the words in its neighbor. And so dog, again, goes through the same encoder, and it gives you a vector. What you want to do is you want to compute some notion of similarity between these two vectors. So the vector for barking and another vector for the dog. It's just like a dot product or inner product of these two vectors with some linear transformation in between. And you get the probability by exponentiating and also normalizing by some other words, and you get the probability. You do the same for some random words that you chose from somewhere else, like chocolate, which has nothing to do with barking. Maybe some dogs are excited about chocolate, but usually if you just choose a random word from somewhere else, there's little chance that this has anything to do with the target word. So you do this to the chocolate word, and you compute the probability with between barking and chocolate. And this is P minus, and this is P plus. And what you want is you want this first probability to go up and the second one to go down. So that's it. And the beauty of neural network is you just tell, this is what we want in a mathematical term. Like this is the exact quantity that we want to minimize or maximize. And then the neural network figures everything out. Because as long as you define all those computational layers in a differentiable way, you can compute the derivative of each one of the parameters with respect to the quantity you are trying to minimize. And then you can use algorithm to actually minimize the quantity you care about by changing the parameters of the network. We use algorithm. We use the algorithm called SGD, or stochastic gradient descent, to use this, but I'm not going into it in this talk. But yeah, that's it. So we ran some experiment. The first one is we artificially generated a huge data set of Morse code, dash dot kind of Morse code from a database of basically sentences. And we wanted to know that if these audio embeddings can recover the semantic relationship between words just from the audio, just from the Morse code. It's really hard, right? It's really hard if you know nothing about the Morse code. Like they just sound all the same. But neural networks can actually do this. So if you look at, before that, I think I have to go over how you actually evaluate this, how you actually validate if this neural network is doing something useful. The way this is evaluated is you have a list of words or word pairs of words, like gem and jewel, which are very similar. So humans give a similarity score of 3.94. Midday, noon, very similar. Automobile, car, very similar. All the way to word pairs that are not very similar, like noon string, rooster, voyage, etc. And you have score assigned by humans. Usually people use crowdsourcing for this, assigned by humans for each pair. And what you do is you run your system to this list of pairs to get the similarity, to get the estimates of similarities, and you compute this correlation between these two lists of numbers. So the correlation is high. If the correlation is high, it means your system is producing something, aligned with what people think of these word pairs. And if the correlation is low, your system is basically not producing something useful. If you look at the correlation, the values of correlation, if you use word2vec, by which I mean this is a situation where you know the exact identities of words. So it doesn't use any audio. It just uses, here is the word bark, here is the word dog, herd, and just compute the word embeddings based on the exact identities of words. So it's kind of like a cheating, but we were interested in how high up in terms of this correlation. So that's a kind of like upper bound of our experiment. And if you use this speech-to-vec, which does rely on the audio input, it doesn't know the word identities, but it can hear what this word sounds like, Morse code, and then it just tries to figure out, the relationship between the words. And it gives you a correlation of 0.272, which is not random, but not great. So yeah, that's the first experiment. the reason why this is not super accurate is, yeah, here. If you look at this, how this network operates is, the audio input is very long, basically. It has a very high temporal resolution, right? If your sampling rate is like 22 kilohertz, there are 22,000, values per second. And even after you convert this to this feature representation, you still have like tens or even hundreds of values per second, which is a lot of value for, especially for RNNs, because RNNs have to go over the input one by one, one at a time, at a time step. And but by the time it reaches at the end of the loop, it just forgets about what it has heard before. So it doesn't have too much memory. Like its memory is just 128 kind of dimensional vector. So it's really hard. So we tried something else. So there's this model called the transformer, which was proposed in 2017 by research at Google. And now by 2018 or 2019, it's everywhere. It's everywhere, especially in NLP. So for example, Google Translate uses this transformer to translate between human languages. It's in production. And a lot of language applications use transformers to process and convert textual information. The way the transformer works is very different from CNNs or RNNs. And it's very simple. It's just layers after layers of transformation. So one cell is in charge of some local transformation of the input and aggregation. So the second layer here just looks at every single input and it just aggregates the information from everything else. But it does this in such a way that it actually determines which input is important to the second layer. This is called self-attention. But the point is, this is a new kid on the block for these neural networks. The transformer just looks at everything. No loops, no pattern matching. It looks at everything and it aggregates and transforms. And you just repeat this again and again to come up with a nice transformation of the input. And it actually works. So I applied this transformer model to this audio embedding task, and it's a lot better in capturing the semantic information from the input. So the correlation is 0.36, which is almost halfway there between complete random and the perfect scenario where you actually know what the word was. And yeah, that's the experiments. And let me see if I can switch this. You can actually, can you see this? Like this like huge blob thing? Yeah, you can actually plot the embeddings on a vector space. And I used an algorithm called tsne, which basically compress this relationship into a two-dimensional plane and map this on this space. If you look at, you see a lot of clusters of words, but if you can zoom in, you find, I think this is most interesting. You see words like few, several, and these are francs, million, pounds. These are like money, currencies, and you have a bunch of numbers here. So what you're seeing is this transformer model actually was able to cluster numbers purely from audio, like purely from the Morse code. And this is kind of, I think this is amazing, because if I were to do this, like if you know nothing about Morse code and if you have to figure out which are the numbers, and then it would take like, I don't know how long, like if at all possible, right? So yeah, you can see the embeddings like this and the cluster of the words. Any questions so far?
And just to add some motivation, we went with Morse code. Originally, we started with just listening to human speech and trying to go to embeddings, and realized that there are so many places along the path that things could get messed up. They were like, well, what is the simplest possible representation of language in audio that we could learn and debug from? And so that's why we ended up going with Morse code. And it's not just bits and dots, it's the audio representation of Morse code.
Well, Morse code is optimized too, and anything in Morse code, you know, in other words, the optimization also gives you a hint at what the word is. There's some frequencies of occurrence.
Mm-hmm. Yeah.
I guess it takes that into account too, right?
Yeah.
So I had a question. Would it be valuable to take Kahn's prairie dogs, where he knows presumably what they're saying, and applying this to that? I mean, would it provide any value?
The prairie dogs?
Yeah, I mean, he has been able to tease out that they have adjectives and adverbs and nouns, and because he can observe the behavior when they're making the communications, he knows that this adverb might be running and this one is walking, and knows the differences of the nouns that they're using. So I'm just wondering how, I mean, what it would be like to take another species communication where we have some idea of what they're saying and applying this.
Yeah, that's a great,
comparing.
yeah, I think that's a great idea. We can, if you have a large data set of their vocalizations, you can certainly apply this to their, quote unquote language, and see what like semantics they have. And in this work, we just use like context, like longer utterances or vocalization, from humans. But if you have things like, if you have any like observation, like what they do with this vocalization and their behavioral, information, then you can actually encode this information as something extra to the network, so that it can better infer the underlying meaning of those words. So there's a lot of work for human speeches, like using text and video, for example, to better encode the language, or also like text and like images to better encode the language and so on. So there are a lot of possibilities for decoding human communication as well, or animal communication as well.
And actually, Masato, you've been thinking a lot about language grounding, and that might be a really good thing to talk about too.
Right. Yeah. There's this kind of growing field in AI called language grounding. So people have been training language models, like those embeddings, purely from the text, but language has to be useful. In order for a language to be useful, it has to have some connection between the signs or like abstract concepts and physical world. So in this growing subfield of AI called grounding and embodied AI, people actually make connection between the abstract languages and also what's actually happening in the physical world. So between images and languages, and between videos and languages, and people even use like robots, like robot simulation, to actually make a connection between those different modalities, what we call modalities of communication. So yeah, it's very exciting and very applicable to animal communication as well.
I guess I was also thinking, the way you compare, say, Italian to English, if you were to take prairie dog to English, if you would see that correlation. And I realize that even though we're assuming that they actually have the similar, they have words. I was reading something about somebody who had a parrot that had learned the name of their dog. And the dog died, and when they got a new dog, the parrot started using that word. So it's hard to say that the parrot knows it as a name or thinks that's what dog is, or, who knows what else, but I'm just curious.
Yeah, I think for decoding animal communication, I think it makes sense to not start from like trying to align, English and like animal language, but we can try to align things like animal vocalization and vocalization from related species, or vocalization and maybe their behavioral signals like videos or some other extra information, so that you can actually know how they correspond to each other. Then we can go from there, because yeah, there's a lot of assumption, by aligning English and Italian, but this might not hold between animal and human languages. But we can use the same methodologies for aligning different signals we get from animals and humans.
With humpback whales, it'd be particularly difficult because humpback whales make sounds that sound like elephants and chimps and wolves and people, and they make all these sounds that it'd be very difficult to not see similarities with other animals. So a humpback whale would be similar to a wolf, but it's also similar to a chimp, but also similar to a human, depending on what their vocalizations are. They're probably Fred could talk better on that, but they're very diverse.
Remember, there's a distinction between how things sound and how things mean. And so there are two types of embeddings that go along with those. There's the acoustic representation, how it sounds, and then the semantic representation with how it means. And actually, a lot of our original work, the models were getting stuck and creating embeddings about how things sounded, not how things meant. What's really exciting about where Masato's been able to push is to get to that deeper layer of like embeddings that represent meaning, not audio encoding.
Yeah, and back it out. In some sense, like applying information theory, when Shannon first did it, he applied rules to the computer and he said, okay, print out English. And it wasn't until he started to get diagram structure that he started to get real English words. But we have this compilation of humpback whale sounds, and we have to back out the rules instead of put them in. So that's the interesting part, is if this is reversible and we can do the inverse problem of getting meaning from the results, that would be really neat.
Yeah, I think there are two aspects. Like in many human languages, like something that sounds similar actually tends to have similar meanings. So what I observed a lot is, I don't know if you can see this. Like this one, thousands and thousands. With and without s at the end, they actually, the same, and they sound similar. So the network, the model here has a very strong bias for how they sound, and this assumption is not actually wrong. It's actually really helpful in encoding human communication, because similar things actually do sound similar, but there are also negative, like false pairs, like cat and car. They kind of sound similar, but they are not. So that's actually what this neural network is trying to kind of decipher. So the transformer model has so many parameters. It has a large capacity that it can actually encode what sound what sounds similar, and what how they should convert this to the meaning representations. So I think that's the very kind of the beauty of those models. I don't think I have much time left, but yeah, I have a couple of slides, but we can just skip this. So yeah, I think to summarize.
I think, yeah, I would say take as much time as you need if people don't have a hard stop, and we'll delay our next meeting. Yeah.
Okay. Yeah, if that sounds good, I can just quickly go over some of the kind of future directions, or natural progression of this work. So far I've been assuming that the boundaries of the words. Where this word barking starts and ends, which is a very strong and kind of unnatural assumption, especially for like animal communication, because you don't even know what words are, and where they are, right? We don't even know if they have anything similar to words in animals. So, but you can actually take a similar approach and just apply this to the raw unsegmented audio. So that's a method proposed by this recent paper from Facebook AI. So what they did is you have like a sequence of encoders, but you just apply this to equally distanted, equally sized chunks of audio. Like no notion of words, no notion of even sentences or phrases or phonemes, but you just apply this sequentially, and you get embeddings for every like 10 milliseconds. And what they did with this model is they tried to classify which two of the embeddings are adjacent to each other, like next to each other, and which two are not. So Z2 and Z3, they are next to each other, but Z1 and Z4, they are not. So they trained this kind of prediction neural network on top of this. And what it learns is it starts to model what type of sound persists and when the sound changes between like phonemes or words. So if you take this network and try to, just continuously apply this, is this next frame continuous or not? Then you get kind of like a graph of from this prediction of this neural network that corresponds to how surprised this neural network is after seeing the next frame. If it succeeds in predicting the next frame, there's less surprise. But if the next frame belongs to a different word or different phoneme, then the network is more surprised. So if you take this graph of like how much it's surprised, you actually can detect where things change and where the phonemes, to be specific, are in this raw audio. So you can actually do segmentation of speech without any supervision. Like you're just, this is very similar to how we train this word embeddings. You don't have any supervision, but you're just trying to have this neural network solve a very artificial, task of predicting the next frame, and then it actually works. So in this kind of proof of concept work that I tried, you actually see the boundaries between phonemes, and you can then cluster them based on how they sound. So in English, you have like 50 or 60 or so phonemes, like and all those consonants, vowels, right? So you get like clusters of similar sounding sounds in English, and if you cluster those phonemes, they are actually words. So this is again some proof of concept where I kind of decoded the English sentence purely from audio, and then the algorithm came up with this kind of cryptic code that corresponds to what the neural network thinks is a word. So yeah, there's a lot of possibility and future directions. I just wanted to emphasize, that this audio embeddings, the audio representation, is the very important first step for any downstream tasks, including translation, analysis, and so on. So I'm super excited to have we have useful, somewhat useful representation of Morse code so far, and yeah, so that's basically it for this talk. So we have neural networks, and the same framework can be applied to segmentation. And if you're interested, all of our code base is public. There's not much documentation yet, but I'm working on it right now. So yeah, you can even like try this yourself if you're interested. So yeah, thank you so much.